Greetings, I am Safina, the team leader of my R&D group su학07. Along with me and my teammates Viru Kasa and Himani Paudale, I did research on partitions in terms of Fibonacci numbers. With the help of our supervisor, Imjang Rosantanim, we were able to successfully end our research, and now we'll start the presentation. So, we aim to study different types of partitions, their nature and properties, and any possible projection plus a new recursive formula. Integer partition is one of the earliest mathematical discoveries and plays a major role in a wide spectrum of human activities and natural phenomena in mathematics, science, and music. So for our research, we took our step from basics, going through most of the famous partition theories, contents, and bijections to get the idea for our research. We studied the contents like bijective proofs, Ferrer's graph, Euler's pentagonal theorem, generating functions, and so on. So after brainstorming for a while, we started to write partition in terms of interesting mathematical numbers like Fibonacci numbers, pentagonal numbers, hexagonal numbers, magic square numbers, and so on. Since it was more convenient for us to use computer programming to compute the partitions, we wrote code for partitions that can be easily modified to get the partition in terms of those numbers. We started collecting the data and looked for the interesting pattern and any noticeable thing among those number of partition and parts, since the Fibonacci sequence exhibits a pattern that turned out to have an interesting and important far beyond what its creator imagined. We decided to focus more on the partition in terms of them. So, a little bit on our theoretical background. So, what is integer partition? Expressing a number as a sum of natural numbers is an integer partition. So, for example, partitions of 3 are number 3, 2 plus 1, and 1 plus 1 plus 1. Partition function. So, it's the number of ways we can express a number as a sum of natural numbers. So, partition function of 1 over 3 is basically 3 because it's 3, 2 plus 1, and 1 plus 1 plus 1. And partition identity. So the partition identities which simulate the number of restricted partitions with condition A is equal to the number of restricted partitions with condition B. And Ferrer's graph. So here are the Ferrer's graphs of partitions of 3. So each box represents 1, and the first picture represents 3. The other one is 1 plus 1 plus 1, and the last picture represents 2 plus 1. So from now on, my teammate Viru Kasa will talk more about the methodology. Thank you.
So starting from now, I will briefly explain about our research methodologies and our one of our main findings for this research, and try to explain how it actually makes sense or what's going on there. So the primary aim of our research is to find as many properties and partition identities as possible. So to make an effective research, we started our research by learning the basics, and after that we subdivided our experimental part of research into 3 sections. The first one is primary data collection, and this part we use different Python codes to generate the partition of a given number. So after that, we collected those data on Excel, and next, after we finished this papers, we went on the content analysis, which is finding as many patterns and identities or any interesting thing worth further study. So after we found those, we tried to explain them using the bijection methods we learned on the very basics of our learning process. So after learning we decided our topic to be Fibonacci partition after we learned the basics. And the basic idea of Fibonacci partition is expressing a number as a sum of other numbers, but those parts should be an element in the Fibonacci sequence. For example, we can take 6. 6 has many partition, but 5 plus 1, both are Fibonacci parts. So 5 plus 1 will be Fibonacci partition of 6. But 6 cannot be Fibonacci partition of 6, since 6 is not Fibonacci Fibonacci number. So 3 plus 1, 3 plus 2 plus 1 are all Fibonacci partition. So if we count this number of partitions, then it gives us the number of partition of a given number with Fibonacci parts. So next, after selecting our topic and collecting data, we went through them and find a few interesting patterns. And one of them, which is a main target of our study, was the difference between distinct Fibonacci partition with odd number of parts and that of even number of parts. And the pattern that existed was it always is 0 or plus or minus 1, as in Euler's pentagonal number theorem. So to explain this, we started by setting many variables and functions to explain as in a very simplified way as possible. And the next thing we did is we picked one of those cases and we made a bijection proof for it. So first, we started by setting a function, which is the function takes a number as a domain, but the range of function is a list. So f of x, it is a list which consists of smaller elements of smaller sets, which are list, and those consists of any partition of Fibonacci number of x in the parts in Fibonacci number of x. For example, if we take 3 has two distinct Fibonacci partition, which is 3 and 2 plus 1. So f of 3 will be a set containing a set which contains 3 and another set which contains 2 and 1. So and then starting from f of x, we further classify two types of functions, and the first one is f of x, but when number of p of x, which means the length of each element is even. For example, going back to the first example, f of 3 is a set containing 3 and set containing 2 and 1. But set containing 3 is not even number, but set containing 2 plus 1 is an even number. So we just pick those with even numbers. So the fe of 3 will be 1 because we cancel the set containing 3 since it is not even. So using this, we also have one more function, and the other function is f odd of x, which is f odd of x is again when the number of p of x is odd. Going back to the first example, f3 of x, we found it to be the set containing 3 and set containing 2 and 1. But 2 and 1, the set containing 2 and 1, its length is 2, so we cancel it, and again we get f odd of 3 to be 1. So once we decide those three functions, or one function and two subfunctions, then we made three possible cases. The first case is when the number of f of x is even, which means the number of distinct partition of a given number is even, and we found out to be evident that the number of distinct Fibonacci partition with even number of parts and the number of distinct Fibonacci partition with odd number of parts is 0. And the other one is when the number of distinct Fibonacci partition is odd. In this case, we have two further conditions. The first one is when the length of the smallest partition, the length of the smallest partition, which means the number of parts in the smallest partition of x, when it's even, then the difference between the distinct Fibonacci partition with even number of parts and that of odd number of parts will be 1. But when the smallest part is the smallest partition has odd number of parts, then the difference will be -1. So after we defined or explained our finding using this method briefly, we went on to find a bijection proof for the first case where the difference between them is 1. Well, between them is 0. So since it shows one-to-one correspondence. So Himani will take off from here and explain about the bijection.
Hello, I'm Himani, and I will talk about the bijection method that we used. For this method, we utilized the Ferrer's graph and the popular method of splitting and merging. So when we have the condition that the number of partitions is even, So we have that number of even distinct Fibonacci partition minus number of odd distinct Fibonacci partition equals to 0. So we can use the following bisection method to use. So here we define f of O or E of n. O or E represents odd or even, which is equal to f of rk plus f of rk minus 1 and so on, where k is greater than or equal to 1, and f of rk is the rk's Fibonacci number. So here f of E of n is one of the partitions of n, and we have the following three conditions. So here, if the Fibonacci index difference between the first two parts, which is rk and rk minus 1 equals to 3 or more, then you split f of rk into its consecutive Fibonacci numbers. If the difference equals to 1, then we merge the first two parts. And then if the difference is 2, which is a bit more complicated case, so what we do is like we go to the very last part, which is f of r of 1, and check if the last part is splittable. That is, the last part should be greater than or equal to 3. The reason why the last part should be greater than or equal to 3 is because if it equals to 2, then 2 will be split into 1 and 1, which won't make it distinct anymore. So it should be greater than or equal to 3. And if so, then we will split it into its consecutive Fibonacci's. If it's not splittable, then what we do is like we check the Fibonacci index difference between the last part and then the second last part. If the difference equals to 1, then we merge the last part and then the second last part, only if the sum is not equal to one of the existing parts. If the difference between the last part and in Fibonacci index difference between the last part and then the second last part is greater than or equal to 3, then we split the second last part into its consecutive Fibonacci. If not, that is the difference equals to 2, then we go to the previous part, that is f of r of 2, and we repeat all these steps for f of r of 2, and we will go on from bottom to top until we encounter any mergeable or splittable part. So I will show you more detailed version using a diagram. So here we have number 21. 21 can be expressed as 13 plus 8, 13 plus 5 plus 2 plus 1, and 21 itself, and 13 plus 5 plus 3. So above we have all the even number of parts, and below we have all the odd number of parts. So for the first one, we have 13 and 8. So the Fibonacci index difference between 13 and 8 equals to 1. So we can merge them, and then it will give us 21. So we come to the odd part. And for 21, it can be split into 13 and 8. So we can go back to 13 and 8. So now we have 13, 5, 2, and 1. So the Fibonacci index difference between 13 and 5 equals to 2. So we can't do anything except by going below the very last part. The last part is 1, and then the second last part is 2. The Fibonacci index difference between 2 and 1 is just 1. So we can merge 2 and 1 and make it into 3. So we come to the odd part. And then for odd parts to go from odd to even, so what we do is, again, we have 13, 5, and 3. The Fibonacci index difference between 13 and 5 equals to 2. So we go to the very end, which is 3. And 3 is a splittable number. So we can split 3 into 2 and 1. So we can go back to before, which is 13, 5, and 2, and 1. Yeah.
So as a conclusion, I want to say that we found an almost bijection between Fibonacci distinct odd number of parts and Fibonacci distinct even number of parts. If we do further research, we look forward to creating a recursive formula to calculate the number of partitions in terms of Fibonacci numbers using generating functions and look more deeply into the partitions. Thank you so much for listening.